Yeah, you may recall several videos ago when I said that there's another section, I believe it was 2.1, and I said, if this is in my class, I'd probably do it at the same time as another section, and this other section is 3.4. In other words, I probably wouldn't have done 2.1. I probably just would have just done 3.4. 3.4 is kind of cool in a lot of ways, kind of dumb in some other ways because it just freaks people out a lot of times. They don't know what to do with it. And so the idea is pretty straightforward. It's all about rate of change. So earlier in the section, in chapter 3, you looked at derivatives. And so you had a function like this guy. And so if we want to know the instantaneous rate of change at 2, we would take f prime of x, and then we drop 2 into that sucker. And you get 18, and that's your answer. Easy to do. If you wanted the average rate of change from, or I shouldn't say from, on 1 to 4, you would put a 1 in and you'd get 8. And you'd put a 4 in and you'd get 48, and 24 is 72 minus 1 is 71. And the rate of change would be 71 minus 8. 4 minus 1. That'd be 63 over 3 would be 21. That would be the average rate of change over that interval. Okay, so that's pretty easy. Should be doing some of that in this chapter. That seems pretty straightforward. You'll see a few problems that are like this, kind of a dealio. I don't know, whatever, something like this. And it'll ask you to approximate the rate of change at certain levels. So let's do it with an ego booster right here. What is the rate of change right there? Why, I'd probably call that 0 or awfully close to 0. Instantaneous rate of change right here. Well, how would I do that? Well, I would kind of just eyeball a tangent line like that, wouldn't you? And then there will be some x and y coordinates here. So you could, for instance, take this point here, which is maybe at 5, 3 or something. And then, of course, this point right here, which is at like 1, 1 or something. And you could use those guys to approximate the tangent slope there, which would be 3 minus 1 over 5 minus 1, which is 2/4, which is a half. So you'll be a few of those where you get to approximate thusly. Okay. Other times you'll be given some data, x and y. Maybe it's years, population. Maybe, I don't know. It could be anything, right? So 1990, 2000, 2005, 2007, 2010, or whatever. And then I'm just making up data here, so no need to get panicked. Goodness sakes. Okay. So if you want to do, like for instance, you could try to approximate the interval here at the instantaneous rate of change at 2007. One way you could do that is to see the rate of change from 2005 to 2007. Which is 11 over 2, which is 5.5. Then you could also take this region here. So it'd be then you could average those. That's 12.5 divided by 2 is what, 6.25 or something. And you could use that for an approximate rate of, or approximate instantaneous rate of change. Okay, not terribly difficult there. Okay. Yeah. Here's another one that will pop up for you, something like this. It says that the position of a particle on a straight line during a 5-second trip is this. So his position, S they call it, is equal to t squared minus t plus 10. And again, our interval goes from 0 to 5, it said. And it said this, what is the average velocity? Well, average velocity is another way of saying average rate of change, because change in displacement or change in position over time is velocity. So at 0, he's at 10. And at 5, he's at 25. 20 plus 10 is 30. So the average rate of change would be 30 minus 10 over 5 minus 0, which would be 4 meters per second, assuming it's in meters and seconds. Okay? And then the second part of the question says, at what time is the instantaneous velocity equal to average velocity? Well, I don't know. First thing I need to do is take it and find the instantaneous rate of change. It's this function right here, correct? I take the derivative of that guy. Well, what it wants to know is when does that thing equal this? I don't know. Plus 1 divided by 2. At 2.5 seconds, that is when your average velocity equals your instantaneous velocity. Okay. Oh, here's another one, I guess. Cool. It says, according to Ohm's law, it says, it says V equals IR. That's the game, where that's voltage, current, resistance. Okay. It says this, where the blah, 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 blah. Assume the voltage is constant, 12 volts. 12 volts. Okay. Now, it says this. It says the average rate of change of current with respect to resistance from R equals 8 to R equals 8.1. Now this looks goofy, so it looks like I is equal to 12 over R is a better way of saying that, because R is acting as my X, so that means Y is going to be my I is going to be my Y. So what I'm saying is this, when you plug in an 8, you're going to get 12 eighths, which is 1.5. When you put in 8.1, you're going to get 12 over 8.1, which I don't have a calculator handy. 12. 1.48. What's the rate of change? It's 1.48 minus 1.5 over 8.1 minus 8, which is 0.1 on the bottom, negative 0.02 on top. And so it looks like negative 0.2. That would be amps per ohm or something like that. Okay? And for some reason I'm just not feeling very confident in myself. Yep, I did it right. Good for me. Further it says, find the rate of change with respect to R when R is 8. And you're like, what do you mean by that? Well, notice I didn't say an average. I mean the rate of change at X equals, or R equals 8. Well, to do that, what I'm going to have to do is find the derivative. That's a key word for derivative. So I prime is negative 12R to the minus 2. Fascinating. That says that the change in current is negative as R gets bigger. Okay? And so when I do this, it's going to be negative 12, of course, over R squared. And I'm interested in the rate of change when R is 8. So I put 8 in here. It's negative 12 over 64, which is for negative 3/16. That's again amps per ohm. Okay. And then it wants to know what the rate of change of R with respect to I. Oh dear, what did they do? They turned the function inside out on us. They said, let's do it this way instead. Well, it doesn't take a rocket surgeon to see that it's the same basic problem. So it's just r prime is 12, negative 12 over I squared when you take the derivative. Same exact thing. And it wants to know what happens when I is 1.5. So negative 12 over 1.5 squared negative 5.33. What does that mean? It means we are losing negative 5.33 ohms of resistance as the amperages increase. Okay? That's it. That's really all there is to 3.4. It's just a bunch of application situations. If you hear instantaneous rate of change and you see a function sitting around, take a derivative. If you hear rate of change at a particular number, like say x equals 8, and you have a function, then you need to take a derivative and evaluate it there. If you hear rate of change and you hear a beginning point and an ending point like 8 and 8.1, they just mean for you to evaluate and find the slope between them. That's really all that boils down to.